Oh, hi, everyone. Thanks for the introduction, and really glad to be here to introduce our recent work on the maskless rapid prototyping of high-resolution G-mode, which is for the grating magneto-optical traps. This work is supported by the DTST, and the target of this project is to develop the technology for fast prototyping of high-resolution G-modes. First of all, I'd like talk about what is MOT or magneto-optical traps. So this is kind of device which use laser cooling of spatially varied magnetic fields to create a trap to provide the samples of cold and trapped neutral atoms. And this is a really key component for atomic clocks, quantum repeaters, and is widely used for providing a time and frequency standards and the frequency of TV broadcasting and the navigation systems such as GPS. So for our project, we are aiming to design and fabrication a type of G-modes to trap Ebeam atoms with a working wavelength of 399 nanometers with the first order diffraction at 40 degrees. And previous reports have provided a range of different type of designs of 1D and 2D G-modes to trap atoms. And for our work based on similar designs, we have a requirement for grating with a period of 620 nanometers and a field factor of 50% and depth of around 100 nanometers. For our project, we have investigated mainly two different types of fabrication process based on focused ion beam, which is FIB. The first one is the FIB-only method, which use a high dose FIB to directly sputter away the material to form the pattern on top of the substrate. Another one is a combination of the FIB and the reactive ion etching, which is to use low dose focused ion beam to do an ion implantation on top of the silicon substrate. The ion implanted region will serve as a hard mask during the RE process. So the unimplanted region will be removed during RE and form a reverse pattern compared to this FIB-only method. So why FIB? First of all, FIB is a kind of device that we do not need to do the mask. So it doesn't require a mask design or fabrication. And with this direct sputtering process, we do not need any photoresist or E-beam resist compared to the lithography process. So it's a relatively clean process, which is quite important for a good performance optical device. And it can achieve relatively high resolution. And compared to a conventional EL or photolithography process, FIB is relatively straightforward. So you can do the patterning directly on top of the substrate. Actually, for our project, we may not even use this metal evaporation process. We can just do patterning on top of substrate. And so we can do a faster test cycle of the prototyping from design, imaging, sputtering until the final measurement in the same system. So we can do the whole process in a short time manner. However, compared to conventional EBL or photolithography, it has a relatively long patterning process. So it's more suitable for small size patterning prototyping. For FIB, we use is a gallium source focused ion beam Tescan 3 layer based on Curtin University, and it has a best resolution of better than 2.5 nanometers, and it is also incorporated with a range of different types of detectors such as top-thin EBS and EBSD. So we can do a lot of work based on this facility. These are some examples that we have done based on the set-specific preparation work and some nano-fabrication work for optical and electrical substrate and the tests. And so the next is measurement. We use a typical deposition of platinum protection layer on top of such structure and use FIB cut to show a better view of the cross-section of the structure. with the tilt correction at EM measurement, we can accurately know the sidewall angle, depth, and the width of the structures we have made. And for the FIB-only method, we have done a range of investigations on different parameters, such as sputtering strategies, control of fill factor, different beam currents, and the control of aspect ratio, so we can accurately control the structures we made. And for the FIB-REM method, the RE is conducted and the ANFF-WA mode node, which incorporates the microelectronic research group located at the UWA. It's a typical RE system plasma lab 100. It has a range of different processing gases and can also do low temperature etching. So we use the CF4 and O2 plasma and select the RE power and duration to accurately control the etch rate and depth. In comparison of the two methods, as you can see from here, we use a relative for the FIB-RE method. We can use low dose FIB, and the duration for FIB is much lower compared to FIB-only method with the same size of 400 micron by 400 micron size grating, and it can achieve relatively good sidewall angle. That means more vertical sidewalls for the grating. However, this method employs two different facilities. It will increase the complexity of the whole process. So based on the requirement of users, so we can choose between those two methods. The two gratings each are with a size of 400 by 400 micron size gratings. That's 1D grating that we have made, and that's cross-section view of the structures. And apart from the 1D grating, we have also designed and fabricated a range of 2D gratings, include this concentric triangle geometry, as well as this chessboard geometry. And our collaborators and other labs have done some optical measurement to show the good performance of the device. We just published our work in the Optics Press, and our collaborators will also present some optical work in a conference later this year. So you're welcome to take a look if you're interested in more details. So for future work of this project, actually we are currently collaborating with ANFF-ACT node to scale up our fabrication of the device. So we are aiming at millimeter size or tens of millimeter size GMOS fabrication, which will be based on Ebeam lithography. And we are also looking for the grant opportunity for an ultra-fast FIB facility, which we expect to be much faster compared to our current gallium source FIB, and expect to be the accuracy stitching to fabricate millimeter sized features. So we are aiming to build a workflow from idea to prototyping until testing, and repeat this prototyping cycle multi-times until we're happy with the results, and continue to scale up the size of the structure with either EBL or photolithography. It will be suitable for microfluidics, waveguide, and some other optical devices. In summary, we have investigated two different types of methods based on FIB for the GMOS fabrication, like the FIB-only method and the FIB-RE method. And we have fabricated 1D and 2D devices and tested them optically. And for more details, you are welcome to contact me or my colleague, Dr. William Ricard, or with our website. Yeah, thanks.
Good afternoon. Thank you very much for that. We have one quick question from Eric. You talked about the lateral resolution using FIB. What is the vertical resolution using FIB, and how controllable is it?
Well, it depends on what type of method you are using. If you do this directly milling, like a FIB-only method, as you can see, we can achieve a aspect ratio to about 1 here, and even higher. It's like the main reason I didn't try more is that for our application, we mainly use this 100 nanometers or 150, that's good enough for us. But it's possible to make it deeper. And for this FIB RE method, you can also make that deeper, like to 120, 150, that's possible. We didn't try too high, too deep of the structure that's based on the current application, but it's possible to make that deeper.
Thank you very much for that response, and thank you very much for taking the time to share your knowledge with us.